First of all, thank you very much for the invitation. It's a pleasure to speak today here at this call. And I must say that we also had some projects for Africa, and I was in Nairobi 3 years ago, and I had a wonderful time, and I was really amazed by the friendliness of the people, and they kind of reminded me of the people over here in Serbia. I think the mentality is quite similar. So I'm coming from BioSense Institute, and it's a really young institution from Novi Sad, Serbia. So what we do is basically data analytics in smart agriculture, but there's much more to that than just data analytics. We started working on the problem of IT in agriculture some 10 or 15 years ago, back when we were an integral part of the Faculty of Engineering of the university. And actually, these two areas is maybe what this region of Serbia is known for. Traditionally, this is a really famous agricultural area, but lately, in the past 5 or 10 years, there have been a lot of startups in IT, and so we're on the overlap of these two areas. What we're especially known for in the European circles are the Horizon 2020 projects. I don't know if you're familiar with Horizon 2020, but it is actually the biggest scientific fund in the world, where we have more than 30 ongoing projects. And that's actually more than all other universities in Serbia combined. So based on this success in Horizon 2020 program, we received the largest project from all of these, called Antares, through which BioSense will advance to the European Center of Excellence for IT in sustainable agriculture. So most of these projects are scientific, but some of them are to do with dissemination of scientific results to the farmers, with acceleration of SMEs around Europe, and so on. So when you take a look at the history of agriculture, there have been quite a few revolutions in agriculture. And if you take, for example, the Industrial Revolution in the 19th century with innovations in mechanics, they also influenced the innovations in agriculture. And then later in the 60s, the Green Revolution started with the advancements in chemical industry with new fertilizers, new types of seeds, new pesticides. And today we've got a really big problem. And so the population of the world will increase to 10 billion people by 2050. And the estimate of the United Nations says that we need to increase the food production for 70% in order to feed the world's growing population. And the technology that we have at our hands today is IT. So those of you coming from signal processing will most definitely see the sine wave here. So this is just an example of a tree line here in Serbia, just a few miles away from me. You can see that there is this spatial variability that is not random. All these trees were planted on a specific date, but yet all of them are different in height. And again, for those of you who are familiar with Nyquist frequency, that you know where to sample the soil to see where this variability comes from. What we want to do here is to really get the information about the plants, to infer where the variability comes from, and then to make all trees or all crops high and equal. So we're using commercially available sensors, but we're also developing our custom-made sensors. We're using robots, we're using drones and satellites to get as much data as we can. And then later we're processing that information within the cloud using machine learning, deep learning, big data analytics and everything. And then we're giving really easy and user-friendly advice to farmers so that the farmers could increase their profitability, they could increase the sustainability of the production and decrease the risks. So this is a rough overview of what the Institute is doing. So let's start from, let's say, nano microelectronics and sensor design. So this is an artistic overview of the sensors that we're developing. You can see here a bunch of like printed circuits, and this one on the left is used for the milk quality. And my personal favorite is this black one called the Batman. And well, at least we call it like that. This Batman has got another version called Robin, it is essentially an optical device, which is a low-cost device, and it's working on the principle that from one of these windows, a ray of light is emitted at particular frequencies, and then it's captured at the second window. So we know how much light we emitted, and we know how much was reflected. And based on the difference between those two, we can have different indices. And based on these indices, we can infer the intensity of photosynthesis. We can know how much deficiencies there are for nutrients and water and many other things. But how this device in particular was invented and designed was that we used hyperspectral cameras first. So there are regular cameras like the ones on your mobile phone, which have red, green, and blue bands. And then there are multi-spectral cameras with maybe tens of different bands, but hyperspectral cameras have hundreds of different bands. So you have just tiny fractions of the spectrum in each band, and you can measure what's happening inside of each of them. So out of all these hundreds of different frequencies, we applied techniques such as feature importance tests and statistical techniques to infer which bands are truly important. So out of, I think it's something like 500 different bands, we took just 4 of them, which are really relevant for the plants. And when we designed the sensors, we managed to achieve low cost, and because we narrowed it down to just 4 bands, and this sensor will cost something like 200 or 300 euros compared to some other sensors that cost 2,000 or 3,000 euros. We're also using LoRa network for transmission of data from IoT devices, IoT being the Internet of Things. And so LoRa is a network that has long range, but not really high throughputs. But that is okay, since in agriculture, you don't need to have a large throughput. You just need to send data, like you need to send like a number. So the temperature is 20 degrees, or the soil moisture is 50% or something like that. And that's really a small batch of data and a small number. So you don't need to have 5G connection for that. But what you need to do, and you need to have in agriculture, is you need to have long range, because you won't have any Wi-Fi or electricity at the field. There was this experiment that we set, which I'll tell you something more about. So there is this electrical conductivity probe that we're often using in agriculture. So we scan the soil using that kind of probe, and what is it's essentially like one stick maybe that's got a circuit. So it measures the shift in the frequency due to different properties of the soil, and it also measures the attenuation of the signal. And based on that, you do that at 2 different levels. So you've got 4 different outputs. So based on that, you usually do zone delineation. So if we transfer this to a machine learning problem, we would say that this is clustering. So we define different clusters within the field, and these clusters have got homogeneous properties inside of them, but each of these is different. We chose to have 4 different clusters within this field, but then we realized that the water properties are the same in the dark blue and light blue cluster, and also they're the same in the red and yellow cluster. So we said that there are 2 different water properties on the field. So based on that, we did some soil sampling, of course, and we put 2 different soil moisture sensors at the field. So using LoRa network and the sensors, we managed to log the soil moisture data, and you can see that this is also connected to the weather station. So you can see how the day and night temperatures follow like a wave. And there is a soil moisture information, and you can see that that's the dark red color. So you can see that there was a spike here on maybe 7th or 8th day, and you know that there was some rain there. So what we did here was, first of all, to log the data from something like 2 or 3 months, and then we developed a machine learning model that uses the rainfall information and temperature information and models the soil moisture. You can see here as well that when we had the rain, the measured moisture climbed, and our predicted moisture also climbed. We were sure that we had a good model. And so later we also included this part of the system. So we modeled the soil moisture according to the temperature and rainfall, and then we took a look at the weather forecast and integrated it into the system. So in the end, we also included like the decision-making parts, and that is, okay, so if the field worker turns on the valve at the irrigation system for like 0 minutes, 30 minutes, 60 minutes, 120 minutes, what will the soil moisture response be? And here, when you have these graphs, you can know that, for example, it's enough to have 60 minutes of irrigation. You don't need to irrigate it for 2 hours, but 1 hour. So you're saving water, you're saving the diesel fuel needed for pumps, and you're also making your production more efficient. So that's just one example. And we're also using mobile phones quite a lot because they're really powerful tools. Here you can see some gadgets like the thermal camera and spectrometer that can also be attached, but a mobile phone itself is also a really powerful tool. So in agriculture, yield prediction is one of the most important tasks, because if you can predict the yield, it means that you modeled the growth of crops really well. And also your fertilizer levels depends on the predicted yield, because if you want to aim for high yields, then you need to apply a lot of fertilizer, and and it goes like that. But what we realized when we wanted to predict the yield is that you don't have to do it in a traditional way. So traditionally, you would have an agronomist with a frame like 1 by 1 meter in size, and he or she would put it above the wheat, and then they would count these ears like the heads of the wheat, and then that number would be related to yield. But what we realized is that if you use a thermal camera, you can see those ears quite better. So they're thick, they're releasing temperatures lower than the leaves that are really thin, and on the wind, they would cool down. So we used deep learning architecture here to detect these wheat ears. And then we just had to do some post-processing and to count them. So I'm just going through a few examples, and we can come back to any one of these, and feel free to ask me anything and interrupt me. So then this is the electrical conductivity probe, and there is the XRF scanner. So as you can see, there are tons of different data sources, and we try to integrate them as much as we can. So for example, you can see the electrical conductivity map. Sometimes you don't know why you've got different soil properties at different parts of the field, but you know that they're different. So you need to sample the soil, or maybe go to the field and to realize why they're different. But this kind of map will tell you where these zones are. So this is the NDVI map that's normalized difference vegetation index, which is like basically when you take a satellite image, it's got different wavebands, and you maybe divide to these, you make like a difference between them, and you get an index like that. So this one in particular would tell you how well the photosynthesis is being conducted. So you've got green parts which are growing well, and the red parts which are growing worse. And you can see that the red parts in the previous image also had low yields. So the yield here at this particular field goes from 2 tons to 8 tons. So if you could manage to erase that and to flatten it, you would have 8 tons on the whole field. And that is the role of IT in precision agriculture. And there is this nice project that we've got with partners from Austria, Germany, France, and other countries. So when you take a look at the protein production per hectare, well, you can see that meat is by far the worst because it's not efficient. From 1 hectare of farmland, you can have maybe cows grazing around, but you'll produce 50 kilos of meat. This is German, by the way. But on the other hand, you may have a bit more protein produced from eggs and a bit more from maize, but soya is the record breaker because from 1 hectare of soya, you can produce 400 kilos of protein. And so some of you may ask yourself, do we need to become vegetarians? I mean, I'm not a vegetarian, but then a time like that may become where we would need to change our diets because, as you can see, some products are not efficient while others are. And this is the reason why soya is so important. And so the European statistics say that Europe is producing only 2.4 million tons of soya, and the EU is importing 32 million tons. So there is this huge need to increase the domestic production. But there is also this high variability of protein content within the field. So as you saw from the yields, they can go from 2 to 8 tons. Here, the percentage of protein can go from 33% to 45%. So again, we want to make everything as high as we can. And also produce of different quality are getting mixed up and sold at a lower price. So if you have, let's say 30% of your field with high quality, like high protein soya, when you mix it up, you'll sell all of that at a smaller price. But here we wanted to offer the farmer a chance to do selective harvesting. So to harvest class A soya and sell it at class A price, and then to harvest class B soya and sell it at B price. So what we're doing here is essentially that we're building a layer cake, as we say. So you have soil conductivity. Here the purple rectangles are the yield map. So these will tell you what the yield was at a small piece of land. And then we've got Sentinel satellite data, which are the squares here. So you're literally making a cake and you're piling up these layers on top of one another. And in the end, you're modeling them all. So the result of this protein and yield modeling is that early in the season, we can predict the protein level of different segments of the field. So in the left picture, you can see that the protein content is lower at the left-hand side. So that should be maybe harvested separately from the rest of the field. And you can also see the predicted yields, which again is used for determining how much fertilizer should be applied. And I'll also tell something more about remote sensing and BioSense. So we are the Copernicus data hub, meaning that we're getting satellite images directly from the satellites, and then we're processing them and we're giving them to different users. So this is one of the maps that we're producing. So this is the agricultural region of Serbia. It's in the north and it's quite fertile, but it's not just a regular map. It's a map of crop structure in the region. So here, this is the cadastre, so you can see different parcels. And what we're doing here is to collect time series of satellite data. So in theory, satellite images are coming every 5 days. So we have a new image every 5 days, but these images are coming in 12 different bands, which are like red, green, blue, thermal bands, infrared bands, panchromatic, and so on. So imagine that as a matrix where you've got like different timestamps and you've got different bands, and that matrix, which can be something like let's say there are maybe 10 or 15 different dates and 12 different bands. So it's quite a lot of data, and you need to classify that matrix into a set of predefined categories. So it could be either maize, wheat, soya, sugar beets, or any other crop that is planted. And for that, we're using random forest mainly, but lately we've started using deep neural networks as well. And these machine learning methods are like methods for classification. So we have predefined categories, and there are these decision trees that are being trained. And in the end, we can get something like that. So each color here denotes a different crop. So green is wheat, purple is sugar beets, yellow is maize, and so on. So you know exactly what was planted on every 10-meter strip of the land. And this kind of information is quite important for decision making for the government, for example, because they want to adjust their subsidies. It's important for like the collectors of agricultural produce, for silos and distributors, because they want to know how much, for example, sugar beets will be there. And also for distributors, fertilizer, because if they know how much land is planted with maize, then they need to get quite a lot of maize fertilizer to answer to the requirements of the market. And also we can mention robotics. So this is a robot that we're using. We're not making the robot, but we're making everything around it, and we're collecting the data from it. So it's equipped with RTK GPS, which is quite precise tool for defining the location of robots. There is a LiDAR, there is a robotic arm that takes the soil samples automatically, and it's also equipped with hyperspectral and multispectral cameras. So another thing that we're also interested in is the quality of produce, because here, as you can see in this example, we're getting different bands, and each of these bands can be understood as a monochromatic image, like a black and white image, but there are like 500 different black and white images layered on top of one another. And it happens that in some of these bands, you can detect bruises and some defects at an early stage, which you can't really see with your naked eye. So in this example, we can locate the bruises and see what parts of apple are going to become stale. So we also had a project with tomatoes. Actually, we're conducting it currently with Wageningen University from the Netherlands. So the problem with tomatoes is that you have this like crown or sepals, which are getting infected by some fungal diseases. And what happens to the crown is that it actually goes upside down, and these sepals, that crown gets into the tomato, and the quality just degrades rapidly, and in the end, you may even have to throw it away. The nice part of machine learning is when you can apply different algorithms and play around with the parameters of neural networks, and maybe do some feature engineering or feature importance tests. But there is this huge manual work that is on the other side of the coin. And so we had a team working on this 2 years ago. So we needed to manually determine the boundaries of these crowns and of these sepals and petals and whatever. And that we used as a ground truth. So as the training data for calibrating the machine learning models. And in the end, we managed to train a system like that, where it would automatically detect these sepals. And then when we detect the coordinates of them in the image, then we can also classify the sepal into a healthy and an infected one. So just to delve a bit deeper into these networks. So we first tried using the fully convolutional neural network. And then it's like when you have large layers of interconnected neurons. So each neuron is connected to each in the next layer, and then there was the UNet, which is quite popular network architecture, and there is the SegNet. And the thing with these networks is that, I mean, they were not designed randomly, but somebody somewhere saw that they're working quite well on some problem, and then it was published, and then somebody else takes the same network architecture and changes it a bit so that it fits another use case. And similarly, we use these networks that proved to be working in different areas, and we had to tweak them and to add new layers. And then we also developed some architectures of our own. And in this case, the fully connected network gave the best performance with over 90% of accuracy in detection of the diseased sepals. So how do we do this? And this is like a question for digitization of agriculture. So this is something that was something that we are doing like for the sake of science and publishing the papers. But I think that the role of applied research, at least at BioSense Institute, is to bring the innovation to the farmer. And this is actually a soil sample in a way that it's provided today. So when you dig some earth and you put it in a bag and you take it to a lab, and they would give you something like that. So this is a paper, and it was generated on a 12-pin printer from like ages ago. And what happens with this information and this paper in particular, somebody reads that, they adjust the amount of fertilizer, maybe add some, I don't know, zinc or magnesium or whatever, and then they throw it away, and it gets lost. All the data is lost. I mean, we had something like 10,000 years of agriculture, and we don't have any data. And it's also a problem with agriculture in particular when we speak about big data analytics. And people usually think of like terabytes of data and gigabytes and petabytes or whatever, but you can do that in car industry quite easily. You can just like put 3 cameras on top of your car, and you can drive around and you get, I don't know, 1 terabyte of data. But to get just one data point, which is maybe a few kilobytes in size, you need to wait for the whole season from the planting of that crop to the harvest. And you need 1 year to get maybe 3 kilobytes of data. And that's why agriculture is really a challenging area for data analytics. But there is this like Chinese proverb: the best time to plant a tree was 20 years ago, but the second best time is now. So if we didn't start to log the data 20 years ago, then it's better to start doing it now than to miss another opportunity. So we designed this platform called BioSense, and it's quite popular here in Serbia. It's a farm management information system. So currently we've got, so this is a bit data information. So currently we've got around 20,000 users, and 1/4 of Serbian farmland is managed through this system. And it's quite easy to use. You can just draw the field boundaries or locate your fields from the cadastre, and then you're getting immediately tons of different information like weather forecasts, like process satellite images. So all of these are vegetation indices, like, well, RGB is like normal, like Google Maps satellite image. There is NDVI, there is normalized difference moisture index, there is the enhanced index, water index, burn index, and so on. So you can actually see what's happening in the field, and you can see how this circle inside the field is the irrigated area where everything is greener than on the outskirts. You can also back this up with photographs from the fields, and there is this module for logging sensor data in real time. And here you can see the yield map on one side and the electrical conductivity on the other side. And actually here at this example, you can see that those circles in the yield. So that's where there is there is a high yield, and you can see that very circle also in the electrical conductivity map. So you can see how everything is related to one another. And there are also drones. So Um, with drones, we're also processing the drone images. There are also some indices, and actually all of them have the formulas, but we won't go through it. So this is the vary index. There is the southern index, DGI, NDVI, and when you combine all that, you again get some layers of data. So the idea is to again split the field into different zones, and this will be your ideal clustering. You know that there are 3 different clusters. They're easily separable, and that's like the ideal case. But what can also happen is that okay, you're going to have 3 zones within the field, but you like misclassify these samples and these areas, and you won't get what you expected. And also the situation is like that these clusters are not really separable. You can't say that one part of the field is growing well and the other is not. It's everything is like, there is this huge like middle segment. And also there is this question of the number of different zones. So sometimes if the field is small, you can have just 1 or 2 zones. And if the field is 200 hectares inside, you can have 5 different zones. So that's also a question. But the reason I'm saying that, and the reason why we design this platform, is to gather the data, and from that data we're getting some knowledge. And this is I think the last thing that I'll go through today. And this is the Syngenta Crop Challenge, which we applied for the first time in 2016, I think, and we came 4th. So this is like the World Cup in agriculture data analytics organized by Syngenta. So we came 4th the first year, but the thing that gave us a big boost in morale was that we were better than MIT back then. So we applied again for in 2017. And in 2017, we came 1st, so we were better than teams from Stanford, Fraunhofer in Germany, Beijing University, Urbana-Champaign, and others. And it also led us to commercialize our technology later. But now I'll tell you what it is about. So Syngenta is a huge multinational company, and they've got tons of data. So they had something like 30,000 data samples. And they have quite a big portfolio of soy varieties. So they have something like 180 varieties, but they don't know which one the farmer should plant and which one they should sell to the farmer. So the goal was to select up to 5 different varieties for a particular farm to maximize the yield and minimize the risk. So we managed to do that and to increase the yield to 5%, which is equal to the increase in profits for 30%. So one is like the revenue is increased by 5%, but because you've got costs, then it's a 30% increase in the profit. And all this is like with a 0 investment, because you're just increasing the yield based on your smart selection of soya varieties. You're not really investing into machinery, fertilizer, pesticides, or anything else. So this system has got 2 parts. So firstly, we would predict the yield and the risk of each of these 180 varieties at the particular location of the field. So as you can see, there are various seeds. And for example, there is this seed number 41, and it's got the highest yield, highest predicted yield, but it's also got the highest risk, which is your standard deviation of the prediction. So you can imagine that as a Gaussian distribution, where you have it's like it's moved, it's got high value, but the variance is quite large, which is like a Las Vegas strategy. You know, it's like investing, like putting all your money on the reds, and you know, you may become a millionaire, but again, you may fail, and you'll fail miserably because this seed is growing only well in perfect weather conditions, and come a bit more rain, bit higher temperatures, you know, it's going to fail. But on the other side, you've got those stable varieties. So these varieties will grow well in drought. They will grow well with heat waves. They're resistant to pests and everything else, but you'll end up earning peanuts. So this is like investing on the stock market. I mean, you can invest your life savings into Bitcoin, and you'll probably, well, you may become a millionaire, but again, you know, Bitcoin may collapse next year. And you can also invest into, I don't know, Coca-Cola, which has been around for 100 years. But I seriously doubt that you're going to become a billionaire just by investing in Coca-Cola. So these are the results that we've got. The biggest improvement that we've got on one field is by a quarter. So we increased the yield for 23%. Sometimes it happens that we choose it really bad. So we got like -8%. But the mean improvement was around 5%, which was further improved in the later years. And 83% of farms can expect the improvement. And so we asked ourselves, well, is 5% good enough? So as this was conducted in the US, well, we asked ourselves, so what is 5% of the US production? And it turns out that you can feed the country the size of Mexico with just this increase with the yield. So we took it on from there and we started producing these maps for Syngenta now. So now we're not observing this problem from the perspective of farmers, which seed should the farmers plant, but we're observing it from Syngenta's perspective. So how should Syngenta distribute these 180 seed varieties? And so we predicted the yields in each one of these micro regions, and these are like 10 by 10 kilometers in size. And this is the Midwest region of the US. And you can actually see that the green variety is suitable for almost any sub-region of the Midwest. But for example, the orange seed variety in the bottom right corner is only good for Michigan and that area next to the big lakes. So now Syngenta knows how to distribute their seeds. And so we also generalized this and we created, we designed a bit more complicated problem. So there are many production goals which we were told about by the farmers. So you want to increase the profit, but there is also the risk in yield, which means like fluctuation of your yields, whether they're going to be high or low. But there is also the fluctuation of prices. Because, for example, the price of maize goes up and down, but the price of wheat is more or less constant. And there is crop rotation because you don't want to plant, for example, sugar beet 2 times in a row. You want to decrease the amount of pesticides, the amount of fertilizer. So this is 7 objective problem. And you want to solve this problem by optimizing your configuration. So there is what to plant where. And so we just limited this problem for 70 fields, which is what our agricultural partner has got. So 70 fields, and we limited the search to just 5 different crops, which they can plant. So it turns out that for 70 fields and 5 different crops, there are as many crop configurations, so strategies, what to plant where, as there are stars in the universe. So there's a really complex problem, and the way we solved it is by using evolutionary algorithms. So this was set up as a multi-objective evolutionary problem, and we collaborated here with Dr. Deb from Michigan State University, who is, I think, one of the most cited people in this area. And this is a multi-dimensional problem, as we said. So this is just shown in 3 dimensions because us humans can't really visualize that well in a 7-dimensional space. But if we reduce everything to the risk, environmental impact, and profit, you can see that there are different strategies, and each strategy carries these 3 values with itself. And you can see how the algorithm converged from the blue solutions to the red ones. So that the final solutions have the optimal trade-off between these objectives. And if you just take a look at the profits and risk, here we produced a few of these strategies, like characteristic strategies. So it's either maximum profit, minimum risk, or something in between, which is like the Sharpe ratio. And it turns out that all these strategies that we came to are better than the company's current strategy. And it's quite better. And it turns out that they can earn around 1 million euros a year more just by using this algorithm. So this is a photo from Nairobi, and that's where we got the Inspire Challenge Awards from CGR and Bill and Melinda Gates Foundation. So we collaborated with CIMMYT Center from Mexico and to make a platform for recommendation of seed varieties in Africa. And maybe I can actually show you how this platform works. So if you go to smartseeds.biosense.rs, you'll just see, so the prototype was from Mexico, and I don't know, you can just pick a random field here. Where are the fields? Okay, so there's one field over there, so you can just click on it, and in a matter of seconds, you'll get the recommendation, what maize hybrids to plant, how much fertilizer to use, and what kind of yield you can expect. So the idea here was to extrapolate that for Africa and to achieve high yields with no additional inputs. But unfortunately, the project was stopped. We didn't get further funding. But on the other hand, we realized that this has got commercial potential. So we developed a system like that here in Serbia, and we got the seed funding for our spin-off. So now we're doing that commercially for European farmers. And just to wrap everything up, this is how we see farmers in the future. Usually when we think of farmers, we think of maybe elder people on the fields or with the tools, but this is actually how farming will look like in the years to come. All farmers will need to have laptops and mobile phones, and everything will be digital for the benefit of farmers, the society, and the environment. So thank you very much.